They're just indoctrinated.
So
They don't even know why Pakistan.
exactly.
Okay, so we're now preparing for Friday's multiple choice test part 2. This test will be 10 questions over these topics. And the BC topics, if we pull the formula sheets that I gave you earlier last week, the first page is all units 6 through 8 concepts. We've been reviewing quite a bit with miscellaneous topics. So hopefully this feels like that we've done more recently, and also polar as well, polar parametric. We've also seen that more recently as well. I do want to just do a quick review on page 2. So maybe it's been a while since we've reviewed tests for convergence. Does everybody have this formula sheet packet? Formula sheet.
Oh, formula packet. Units 6 through 8. Yep. I'm not really.
When I put that thing over in
Lazy,
the
but-
PC.
Would be.
That was a low light. That was a low light.
So I want to go over this because I think this is I just try to compact everything in one page so we can kind of just have a way of quickly reviewing through. So test for convergence, we have 7 or so of them. I would say root tests and telescoping series, these are less likely to show up on the AP exam, but I still want to, those are relatively easy, so we can kind of just, shouldn't take too long to go over. But first is end-term test. This should be the one that we try to use first because it's quick. It doesn't always, a lot of times it gives us inconclusive results, but it's a quick one to test. So the test for, this is only a test for divergence, and it says that if the limit as possibility of my rule of sequence does not go to 0, then I'm guaranteed to conclude that the series diverges. And sometimes you can, going through this test can potentially allow us to avoid more complicated tests that could work as well, but it will take a lot longer. So end-term test is a nice and quick one for us to just see the series divergence. Now, if the limit does go to 0, then we have to look at something else. So that is the annoying thing about the end-term test, is that it doesn't always give us a conclusive result, but it is still worth the time to go through it because it's quick, even though it doesn't always give us a conclusive result. If the limit does go to 0, then we know that, okay, it could converge, but we need a different test to make further justifications. Next is geometric series tests. If something is in the form of like a ratio value raised to the n power, like 1/2 raised to the n, or 2 raised to the n, then just look at that common ratio to see if the absolute value of that common ratio is less than 1. If it does, then our series will converge. If otherwise, it diverges. So if the absolute value of R is greater than or equal to 1, then the series will diverge. But if the series converges, we can also find the sum. So sum for geometric series is a sub 1 over 1 minus R. Next up, p-series test. If something's in the form of 1 over n to the p, like for instance, 1 over x to the second power, or 1 over n to the first power, we know that it converges if p is greater than 1. If it's like if p is 3/2 or 2/3 or 4/3 or 6, converges, but otherwise it diverges if it's 1 or 1/2 or. Now, if p is in the negative value, then we should bring it up to the top and make it go through the end-term test. So our p value for p-series test should be in the denominator, and it should be a positive value. Integral test. Typically, if something looks like a use substitution problem, that typically is a good indication that's probably going to be an integral test. The conditions are the series needs to be positive, it needs to be decreasing, it needs to be continuous, starting at some point. So once you can identify that starting point, from that starting point, it should be continuous. If the improper integral from 1 to infinity, usually it's from 1 to infinity, but you can adjust that lower bound to be a different value. Usually it's 1 or 2. But if my improper integral can diverge, can converge, or if we can produce a real number, then we know the series can also converge. If the improper integral goes to infinity, then we can say for sure that the series diverges. We don't know what the sum is, even if it converges. All we know is that it converges if it goes to a real number. Limit comparison test. This is when a series looks like it's in the family of geometric series, or it looks like it's in the same family as P series, but something is making it quite a little bit off. Then we go through a limit comparison test, which is finding a comparison partner that is in the same degree as what we see, like a parent version of the one that we see. And limit comparison test is we just take the two series and divide them over each other. It doesn't matter which order. And limit as n approaches infinity. If the limit as n approaches infinity of that fractional value approaches a real number, then the series will either converge or diverge, depending on what you know about the comparison partner. So if the comparison partner is 1 over n squared, then you know that series converges. And if my ratio as n approaches infinity equals a finite positive number, then we know that this is a valid test. And whatever my comparison partner has, then I know I can make the same conclusion for that, for the series in question. Direct comparison, we typically, this is more of a last resort. We typically don't rely on direct comparison unless like there's sine or cosine involved and it just feels strange. It doesn't quite fit into a rational function that would be good for a limit comparison test. And I'm also choosing a comparison partner. But if my comparison partner is one that converges, then if I can show that the series is less than my converging partner, then I know that the series in question must converge as well. If my comparison partner is a diverging series, then if I can show that the series in question is greater than the diverging series, then I can also say that my series will diverge as well. Alternating series test. If I have an alternator, then my series it's easy for us to tell if the series converges. We should basically go through nth term test, and if we can show that this limit of the rule of sequence goes to 0, it converges. Normally, this is not good enough for a series to converge, but if this is alternating series, then every other term is getting subtracted out. So this allows, this is good enough to converge because every term is getting subtracted out. So the condition for AST is a little bit easier than a non-alternating series. There's 2 criteria for alternating series. The limit as n approaches infinity of the absolute value of a sub n has to go to 0, and then my a sub n plus 1 has to be less than or equal to a sub n. Ratio test. This is the one that we've seen the most recently of. Anytime we're doing Maclaurin series or Taylor series problem, we always go through ratio test. So we take a limit as n approaches infinity of a sub n plus 1 over a sub n, absolute value of that. If we can show that it's less than 1, we know that the series converges. If it's greater than 1, the series diverges. If it's equal to 1, it's not a good test. The test is inconclusive. Root test. If my entire expression is raised to the nth power, then root test is good. So I can take the nth root of that expression, get rid of the root, get rid of the exponent, and then evaluate the limit and see if that will be less than 1, greater than 1, or equal to 1. Very similar conditions as ratio tests. And telescoping series, This is a series in which most of the terms cancel out. And if I can get my series into the difference of partial sums, then that's usually a good indication that it's going to be a good candidate for telescoping series. All we need to do is to run through like 3 or 4 terms, and we should be able to see a pattern enough where all the terms cancel out, and whatever's left over is going to be your sum. And then at the bottom of the page here, these are good ones to memorize. We should know our Maclaurin series definition. We should know our Taylor series definition. We should also memorize Maclaurin and Taylor series expansion for the following. Sine, cosine, and e to the x. These are the most common ones. Inverse tangent, this is probably not going to be the one that shows up. But we should know this one as well. 1 over 1 minus x. This is basically a geometric series. This is my first term. This, whatever's here is my common ratio. And I can just keep multiplying by the common ratio with my next term. So we should know this one as well.
Sweet. With these MCs, like what's interesting, like on the main test? Because like was yesterday like an accurate depiction of how fast we should be going? Or...
No, I'm kind of working your, I'm kind of helping you, work your way up to the speed that's needed. So on the AP exam, you're going to start off with multiple choice, non-calculator. And it'll be 30 multiple choice in 60 minutes. So it feels like a lot. However, there are probably going to be enough of the multiple choice questions that should be relatively quick, that you can be able to get through in like maybe 30 seconds or so, which will allow you to have more time. Technically it's 2 minutes per problem, which doesn't sound like a lot, but the easier problems you get through fast, and you can save, the harder problems I will give you maybe 4 minutes, 5 minutes per problem. So, that's the first part, and then you move on to the calculator portion, which is 15 multiple choice in 30 minutes. And then your FRQ section, you're given 15 minutes per problem for you. So, and then you can divide it out however way you want to, but on average, they'll give you 15 minutes per problem. So that's the setup. Yeah.
So is like 15 minutes like a suggested pacing, or is it like?
Yeah, it's a suggested pacing. They'll give you the calculator portion comes first, which is 2 FRQs, 30 minutes. After 30 minutes, you can still work on the FRQs, you just don't have the calculator anymore. And then after you break the seal, I'm sorry, there's no, everything's going to be on, is on Blue Book now. So they will just give you the ability to look at the next 4 questions. And then so 4 FRQs, and then you have 60 minutes to finish off the rest of the test.
We can still work on it.
Yeah, you can still work on 1 and 2, you just can't use calculators.
If it's on Blue Book, do we bring a calculator or did they give us one?
Yeah, you'll get a handheld calculator.
Okay.
So after non-calculator section, they'll ask you to bring up your calculator. You can use your calculator, and you'll get a break, and then you'll start the calculator, put it away, and do the non-calculator section.
Okay.
Yeah.
You said we will get a handheld calculator. Does that mean we will provide it?
No, you have to bring your own calculator. Sorry, you got to bring your own calculator.
I don't know if Blue Book would force us to have that calculator.
We can probably get one up.
I think they could do it.
We can get the guns on. No,
Really? Yeah, I don't know.
I didn't know that.
Yeah. Sometimes, like on the SAT, it gives us the Desmos calculator.
It's like if I open the folder,
Yeah, exactly. That's it. It's so easy. So it doesn't.
Good. I'll double check that.
we can get the Desmos graphics calculator on Limit.
That's what they say. I don't know. Have you guys heard about?
Well,
Wait,
So I took the SAT on that. They had to get the exercise.
I'll ask, and I'll find out. Okay, let's go to page, any other questions? So I wanted to give you a way so that you have to do every problem in the packet, but the numbers are messed up because I copy and pasted from,
Do I need to get a 4B or are we giving out something?
yesterday, you didn't get one. Okay, that's fine. Does anybody need, does anyone else need four B?
Eventually, you know what college you're going to? I don't know. I don't know if I want to go. I'm just gonna leave stuff there tomorrow.
No.
I really. Yeah. I don't.
So, what I want us to do is, tomorrow I'll be checking pages 1 through 17, but it'll just be the first and third problems from each page. If there's only 2 problems on the page, then just the first problem. So, first and third problem. Okay. So don't look at the even and odd. Just look at first and third from each page.
Is it second and fourth? Oh,
Okay, so let's start with 14. If I have a variable raised to a variable, the strategy is, okay, I want to get it into numerator and denominator, I can do L'Hopital's rule, but it's not quite set up for it. So this is kind of like log differentiation. We take the log of both sides, or we make it into a log equation so that we can use the exponential property to bring it down.
Is it not this one?
Yeah, it is equal to 1, but technically the way to work through it is if we can treat this as y equals x to 1 over x, take the natural log of both sides, force that exponent to come down, and then force it into a numerator and denominator, evaluate the limits, we get infinity over infinity, which gives us the green light to do L'Hopital's rule. And then finally, we know ultimately that is equivalent to natural log of y, and y is equal to 1. We're skipping 24, but 24, we should be able to recognize, oh, this is going to be U substitution doesn't work. So integrated by parse tab method to handle integrals of 2 different families of functions that are being multiplied.
Okay. For number 14, I'm
Yeah.
a little bit confused how we get to ln of y, get from ln of y equals ln of x over x to taking the limit of that, then like what allows us to do that? To just like take the limit of that. Like how is that like equivalent to the original? That's my question.
So let's say we had y is equal to the limit as I take approaches. And then I'm just doing this. I'm just taking the natural log.
Oh, yeah, yeah.
And I'm getting this cleaned up. And once this ends up being 0, then I'm just moving through and solving for y.
Okay.
Yeah.
Oh, you bring it back. Okay, yeah. I want y equals 0. Okay, yeah.
Bring it back. Okay, 26. This is Calc polynomial centered at 8. So that's our formula for Calc polynomial. All of our C value can be replaced with 8. So ultimately, if I can find f double prime of 8, then I can fill that in with the proper coefficients. And I'm ultimately just trying to figure out what this number is, if this is my coefficient. So even though we're skipping the evens, I'm still just going to quickly talk about, what category of problem that it falls under. Like if you look at 28, you see real number to improper to infinity. This is an improper interval. So since my f of x is x to the 2/3, f double prime will get us down to -2/9, x to the -4/3. Clean that up, plug 8 in, get the numerator portion of my coefficient, but make sure I still include the denominator portion of my coefficient, and then get it all the way cleaned up. Page 2. I want to talk more about this tomorrow. I noticed, after I graded your Taylor series test, I noticed that some of us kind of have some trouble distinguishing between, okay, when do I do alternating series error bound versus Lagrange error bound? So tomorrow I'll go through and talk a little bit more about, if they don't tell you, what are some context clues that we know to do alternating series test error bound or Lagrange error bound? They're kind of similar, but also there's some distinct differences, but I'll do that with you tomorrow. This one, 38, they tell you is Lagrange error bound, so that's nice. Sometimes the problem doesn't tell you, and we'll tackle those problems tomorrow. So this is our formula. We know we have to involve the n plus first derivative of the degree that they are referencing. But it says you wish to estimate e to the x over the interval absolute value of x is less than 2 with an error that is less than 0.001. The Lagrange error term suggests that you use Taylor polynomial with degree at least. So we have to set everything up. We know that x is less than absolute of x is less than 2, so we're going to make that as great as possible. So we'll make that e squared. We'll leave n alone because we're trying to figure out what n value will allow us to still be less than 0.001. So we can plug this in our calculator, replace n's with x's, and then just look to see when is that, how great of an n value can we go down and still be less than 0.001. So we plug that into our table and just scroll through, we should be able to see, okay, we can have n all the way up to 10 and still meet the criteria of less than 0.001.
You just graph it.
I think the table is I think you could graph it, but I think it's easier with the table because you can look at the y value.
How do you vote for the tables?
Second graph.
Okay.
I can try it too.
We use the equation solver to.
You can use anything you want in your calculator. They won't check it.
Yes, and it's one derivative will always be equal to x, that's why that. It's a yes.
All right, 41. Mhm. I entered it in like this, e squared over x plus 1 factorial, and then 2 to the x plus 1. Let's see. And I did second table here. So we want something that is less than 0.001. So 10 is the first instance that I have something less than 0.001. 41, we do need to recognize the Maclaurin expansion for cosine of x. If we understand this is cosine of x, we should be able to look at that and recognize, oh, that's cosine of x. Okay, next page. Sorry, let's skip this one. This is a little messy here. Just do 18. 17 is a little messy here. Just do 18. Sorry.
Yeah, there wasn't any 17 anyways. So
Oh, there wasn't a 7. Maybe I. Okay, yeah, just do 18. Sorry. Anytime you see your denominator is either factored or could be factored, that's an indication. Okay, we probably need to they probably want us to split it up into the sum of two fractions, and then have an easier time with the integral rule, which allows us to just go through u subs or natural log. But careful, the 2x minus 1 is not as easy and quick as the x plus 5. You can't just say, this one you say, well, natural log of epsilon is x plus 5. The 2x minus 1 is going to produce its own coefficient. So we do have to be a little more careful with that. Go through a full u substitution there and understand there's going to be a 1/2 that's going to come out of that process. once we find our A's and B values, we're gonna go through our use substitution. There's gonna be another 1/2 that's going to come out of, that we gotta keep track of. Start with the ratio test, find your potential interval of convergence, and then test your endpoints to see whether we're going to keep them or whether we're going to not include those endpoints.
Factorial distribution.
Yeah, typically, yeah, if I see factorial, I'm always jumping to ratio test. But if it's asking for interval convergence, it's always ratio test. Yeah, it's always the ratio test. $26. Expand out cosine of x, and then you can distribute the x squared through. $26. Go back to 20. Sure. 22. Okay, so we can get through one or two more, page 5. And then let's finish with 92, bottom of page 5. Oh, right here.
Yeah.
That just means x is a value. That's all real numbers between. It's an element of negative and positive infinity. It just means that x lives in that interval.
X is an element of like the set.
Yeah. Of the
Yeah,
of all the numbers.
in this case, yeah. Well, we see that. So I call it the fancy art, the all real numbers.
I don't think so. Like this, I haven't seen it
Yeah.
from College Board. I don't usually see that, but.
I was in AP pre-calc.
Oh, okay. It's possible then.
Actually, I don't think it was on the AP exam. Maybe it was like an MC. That was like theory based. But I don't think that. Okay.
Good. It's, I think it means x is an element of the interval from negative infinity to positive infinity. So it just means, I think it means the same thing as this. Yeah, built-in Desmos graphing calculator is available on Blue Book platform for certain AP exams. Bio, Calc AB, BC, Chem, environmental science, macro, micro, physics. However, Desmos is not available for the AP Stats exam. Students can use approved personal or school-provided calculators on those exams.
That's supposed to be we got it.
That's what's.
I don't know. But you can use your own calculator for AP Stats.
Like a graphs the area.
So we don't have to bring our own calculator. Will they let us use our own calculator?
Yes, I think you should still bring your own calculator, but it's nice to have Desmos as another
Yeah.
option.
Desmos is good for graphing, like it's faster to type in functions. But it's only good for graphing.
Yeah.
We can do this for Boston.
Okay, all right, come get your phones. Tomorrow I'll check pages 1 through 17, first and third problem. I'll send out a reminder this afternoon.
I'll look at that, tell you what I. Because there's a way we can do it.